Excellent. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and we thank you for math. Help us to say some more things about it. Amen. All right, here we go. So, so you already know what a supernumber is, roughly speaking. And so basically here's the deal. If I have a function, and something like function from RPQ to, say, some set of supernumbers, lambda, then that function is super differentiable, all right? Or you could say it's G, usually I think G1 at the point P or something like that. We could say at the point, what's the point? A comma B, sorry, no pun intended. G1 is well, F is an element. And what I mean is, really I want to think about this on some kind of open set, so you have this G1 condition on the whole thing. But, so I guess I should tell you the set, so if I have like x comma theta, an element of RPQ, then that implies the length of this thing, all right, is equal to a sum, I equals 1 to p, of the norm of xi plus a sum, j, or let's say alpha, rather. Alpha equals 1 to q of the norm of theta alpha. So, in the thing you watched before, I described the norm of a supernumber. Now I'm describing the norm of a PQ tuple. P even coordinates, Q odd coordinates. And we just take it's kind of like the usual Euclidean norm, except I'm using, in some sense, the one norm, just to keep things simple. You could use the square root of the sums of the squares, but it would just, I mean, why bother? Okay, so definition. If f from RPQ to lambda is Frechet differentiable at a comma b, and so Frechet differentiable at a comma b, I guess I better pause right there. What that means, of course, is that the limit as h goes to 0, right, of f of, let's say, goodness gracious, I had a comma b, let's just call that collectively a. So f of a plus big H, all right, minus f of a minus d a f of h, all divided by h, is equal to 0. Now, of course, I can't do that. E's no allowed. Norm. Sorry. Cheers humor is less and less relevant to our daily lives. Yes. So Frechet differentiability in a Banach space. Banach space, what I mean? I mean that there's a norm, but it's not finite dimensional necessarily. I mean, this is infinite dimensional. But there is a norm. And so with respect to that norm, we can define limits, continuity, and so forth. And in particular, Frechet differentiability, which just means that there exists this dA, f, which is itself, by the way, linear. Now, Frechet differentiability means that this is linear with respect to what? Just with respect to the real numbers here. Okay. But I think you know what I'm about to write. So this is, if you have this real differentiable function on RPQ, and if what? What does it take for f to be super differentiable?
I don't know.
Ah, very good. So, DAF, all right, of, let's say, CH is equal to C DAF of H for all C in what I was calling R sub C, the commuting real supernumbers. And H, I'll use the notation, say H comma K and RPQ. So I would, sometimes in my thesis, I might call this lambda 0 R linearity. So it allows you to pull out commuting real superscalars. That's super differentiability in a nutshell. What that means, okay, is that you can write the Frechet derivative, right? Acting on H as a sum. Let's say big M equals 1 to P plus Q of partial F, H M partial F partial ZM, come on, at the point A. And that you could break up into a sum, little m equals 1 to P of H upper M partial F partial XM plus K alpha partial F partial theta alpha. Sum alpha equals 1 to Q. So you've got these partial derivatives with respect to commuting coordinates and partial derivatives with respect to anti-commuting coordinates. And they exist. Super differentiability implies the existence of both of these sets of super partial derivatives. And the calculus, the partial derivatives of all kinds of fun stuff, like if I have partial ZM of F times G, and these are, they're taking their values not in the full set of supernumbers, but in either even or odd supernumbers, so they have well-defined parity, all right? Then there's a graded Leibniz rule, like this. So partial F partial ZM G plus minus 1 to the parity of F, parity of M, partial, goodness gracious, F, partial, and this is an example of what I was talking about earlier today. You have to maintain the order of things. All right. There you go, and you can prove that straight from this up here. Basically what happens is, in order to get a coefficient next to the H, you have to, you end up needing to change the order of these terms, but not those terms, when you look at that. I derived this for them. I think that's, I hope that's taped. I don't know if I did that in the, I did some stuff for them in the day where we did the research day during finals week. That I didn't tape. So if I did it in that day, it's not taped, but you can derive this. It's in my thesis among other things. It's not hard.
Okay, so H is just a vector.
Yeah, I use H as like a big notation for, H and K. Now that's a P. That's a P.
P vector.
That's a P vector. That's a Q vector. Those are both, but P vectors and Q vectors of supernumbers.
Oh.
So.
Oh, really? Okay.
Yeah.
Okay.
So it's actually a vector of L1 sequences, perhaps.
Okay, that notation. I don't know if this is the notation you used in the video I watched. I mean, is that's supposed to be boldface R?
Yeah.
Okay.
RPQ. It's a flat superspace of P even dimensions and Q odd dimensions. So anyway, that's
So that's finite dimensional supernumbers, and capital lambda is infinite dimensional.
no,
potentially.
no. Everything's infinite dimensional here. Finite superdimension all around.
Okay.
Fair enough.
It's just RPQ is tuples of supernumbers, and the first P are even, the
Right.
Q are odd.
Yeah, I think we could say it is a free lambda 0 module.
And lambda is just an arbitrary supernumber.
Yeah, lambda. No, I'm using lambda. Yeah, here I was being somewhat vague. So I've described. So basically, lambda is things of the form z naught plus zi a to I summation implied. You know, summation implied. I also could call this C sub C, direct sum C sub A, you know. And then like the real super numbers, you can break it down further. That's R sub C, direct sum I R sub C, plus R sub A, direct sum I R sub A.
Okay, so
For what it's worth.
So your function's taking as input supernumbers with real coefficients and outputting ones with complex coefficients, or
Well, let's see here. Very good. At this point, we can put this away. So that's your basic super differentiability. To talk about what's a supermanifold would be a Banach space, which permits local bijections to RPQ, and an atlas which covers it, and then the transition functions between charts in that atlas must simply be super differentiable. It's a supermanifold. Sound familiar? That's the beauty of our viewpoint, is that we can really pretty much just use the usual viewpoint with super numbers replacing numbers. Now, back to your question of what on earth do I mean by I think that's up here. So I use complex coefficients for various reality conditions. So this is, I'm not sure how much this has to, okay, so let's look up here to start with. Sorry. So up here, this is just generically supernumbers. I allow complex coefficients, but I insist that the norm be finite, okay?
okay.
But there could be infinitely, this is a multi-index, right? So that includes the body and the soul and everything in between. Then the real ones, well, those would be these guys, but the reality condition. Z conjugate equal to Z. Now, Z conjugate equal to Z at the level of Grassmann components is rather complicated. Because the conjugate on the Grassmann generators, it reverses their order. All right? So like the superconjugate of Z times W is superconjugate W times superconjugate Z. And so to put the Grassmann generators back in order, it costs you a sign. And the sign depends on whether you have evenly many or oddly many generators. So what the reality condition looks like at the level of the Grassmann components is different for the even and the odd components. For the even component, for the odd components, well, in particular, it says for the odd components there's 0. So if you so if I look at like so this S is the parity, so like the S equals 0 or 1 mod 2. So 0 would be the even supernumbers. Even supernumbers don't have odd numbers of supergenerators in their expansion. That's just the nature of if they commute with everything, they can't have oddly many generators that would violate the commuting condition. And so, long story short, we have to have the odd coefficients are all 0, right? So that's what an even supernumber looks like. Actually, this has nothing to do with reality. This is just the even-odd content. So even supernumber, odd supernumber, and actually does have evenly many or oddly many generators built in. Now, what does the reality condition then look like? Even supernumbers only have even components, and so when you look at the reality condition term by term, because you have evenly many, when they flip around, you end up with actually just the condition that z star equals, like you end up with the components are self-conjugate. In other words, for an even real supernumber, the components honestly are honest-to-goodness real numbers. However, when you look at the conjugation condition for odd supernumbers, odd real supernumbers, you get pure anti-conjugate. I mean, like zi is equal to minus zi star and so forth. In other words, they're pure imaginary. So a real supernumber, I would love to tell you that they have real coefficients. It's just not the way it works for us. And Alice-Rogers, so for us, the basic thing is the Grassmann generators are their own, like, we say that Z1 conjugate, A to 1 conjugate is equal to A to 1. All right, that's at the base of everything in our definition of the conjugation. She says otherwise. Like Alice-Rogers says, like beta, her beta I conjugate, it's like I times beta I or something. And with that with that condition, and she's got a few other conditions, she manages to get real supernumbers having real coefficients. I'm content, though, to have this condition, to have pure imaginary. I mean, there's always a clear way to get to a real number for a real supernumber, right? Like, yeah, okay, fine, it's imaginary, but you and I both know it's very easy to get to real, to get to something real from this if I need to. Okay. All right. Are we good? So that's just the background. I'm not sure that has much, if anything, to do with what we're doing. I mean, okay.
With what we're doing in
The rest of what I'm talking about today.
like what you have been talking about, or what you're going to talk about?
What
or
I'm going to
both?
talk about. Yeah.
Okay.
I do appreciate this. This is nice. All right. So have you looked at Alice-Rogers' paper about the non-abelian super? She gives an example over like
Well, regardless, the answer is no.
I see. Okay, so here's the paper we were working off of. In this paper, she looks at these things. 3x3 matrix, upper triangular. And she's working over what's called B sub 1, upper 1, 2. What that means, 1 even dimension, 2 odd dimensions. However, just 1 Grassmann generator. So her odd supernumbers are just of the form like A plus B eta. That's it. She's only got 1 Grassmann generator to work with. And so then she forms a supermanifold of these things, and then she mods by cosets of these Grassmann integer cosets, and she proves that in fact it's a she builds an atlas for the thing and finds overlap functions and argues that it's a supermanifold, and not just that, it's also a supermanifold which is fundamental group D, and So the point here is that this gives you a compact supermanifold with a non-abelian fundamental group. That's interesting in a sense because the non-abelian aspect of it is very much in the odd coordinates, and in the other approach to supermanifolds, I'm not entirely convinced it's possible to put non-trivial topology in the odd coordinates. Like the odd components are necessarily they're not. It's not the topology is not even Hausdorff in the other approach. It's like projective Hausdorff or something. I mean, there's other in the other way of doing things. Essentially, the topology of the supermanifold is the topology of the base manifold. The base manifold is the or you might call it the body manifold. Like just strip away the odd part. So that's I think there are theorems to that effect that the topology of supermanifolds in some sense is not interesting because it's just the topology of the base the body manifold. And what I'm saying is this is an example where it's not the case. The topology of the base manifold and the topology of the supermanifold are in fact, the body manifold and the supermanifold, they're not the same. So that was the genesis for that research day, right? And here's what we did. We just tried to mock what she did. And what she does, what Alice Rogers did, was to play off what's called the Heisenberg group. What's the Heisenberg group? You take the 3x3 matrices like this, all right? And like that. And you matrix multiply them. When you matrix multiply them, you get this. That makes sense if you take your ABC from a commutative ring. They could be real. Now, if you take them from the reals, then you have the real Heisenberg group, all right? The Heisenberg manifold, which is well known, it's one of Thurston's 8 model geometries. It's a nil manifold. It's formed from quotienting the Heisenberg 3 manifold by the Heisenberg integer discrete subgroup. So this is a discrete subgroup of this Lie group, right? Which means it's closed. And then there's a theorem that says if you take a Lie group and you quotient by a closed subgroup, the resulting quotient is a manifold. All right? So that theorem tells you that this quotient's a manifold. And it's kind of an interesting manifold. It's this Heisenberg manifold, is it called. All right, so it's interesting. These are actually some kind of subset of the affine 2 group for what it's worth, these things. But that's kind of aside. All right, so what we became... Now, so if you look at what she's done in that paper I just put away, she's looking at sort of the same thing, right? But the x is even, but the y1 and the y2, those are odd coordinates. So she's changed the rules of the game a little bit. She's not just taking all ABC from a particular commutative ring, right?
Yeah.
She's playing this game where she's taking x1 even, y1 odd, and then y2 odd. And in order for it to still make sense, it must be that when you multiply those two things, so let's just kind of like think through it a little bit. So what did I just, so what the game she's playing is basically even, odd, right? That pattern. And likewise, this would be even, odd, odd, right? So look at this. X plus A, what is it? Even plus even. Is even plus even even?
Yeah.
It is, yes. Isn't it funny that what you know about integers is still true here? How about odd? We've got an odd plus an even times an odd, right?
Yeah.
Plus another odd. Indeed, that's odd. That's still true for these things, even though I know you're thinking, you might be thinking about integers, but you'd still be right. That's the structure. Even times even is even. Odd times odd is actually an even variable. So like the parity function kind of tells you the parity of f times g is the parity of f times plus the parity times g. That's the algebra. So only the product of odd and even. I mean, odd and even is odd. Even and even is like 0 plus 0 is still 0. Odd and odd, 1 plus 1 mod 2 is 0. So like odd times odd is even. But anyway. So the point is, the product of two of these kinds of special parity pattern matrices works out to the same parity pattern. So you're still left with even, odd, odd. So, in fact, it makes sense. You could say it's a supergroup. All right, it's a group which is also a supermanifold. In fact, it's a super Lie group. And then what she does, all right, now, of course, what she does it for the finitely generated case, right?
Yeah.
So that thing I was showing you on the second page, she's literally taking a finite dimensional Lie group. It's also a finite dimensional Lie group in the ordinary sense of Lie groups, like we've studied, well, other people studied, which is a manifold with group structure. Okay, it's not a big deal. Sorry, it's not a big deal. But it's a finite dimensional Lie group, and so you're modding by a discrete subgroup of a finite dimensional Lie group, which is a manifold. And she's using nothing more than just regular finite dimensional manifold theory here to make these conclusions. We have no such luxury. I'm working with infinitely generated supernumbers, right? So I want to follow what she's doing as much as I can, try to generalize it, and then face the music when we need to. So here's what we did. We just said, okay, fine. We're going to try that out. We're going to try to do the same thing. And so I just showed you half of it. It still makes sense, whether they're finitely or infinitely generated.
Yeah.
All right? Starting point. And then we thought through her quotient. So what did she mod by? Like the ordinary thing, you mod by integer matrices with integers, right?
Yeah.
She modded by Grassmann integers. So what's the quotient look like? It's up there. See that? Up here. So the coset that's representative is x, theta, beta, is I can have like x plus z1, theta plus beta z1 plus z3, and then beta plus z2. I don't think... Oh, right, that's fine. I thought I needed a z4 for a time, and then they talked me out of it, and I was happy. Now, what are these z's? These are Grassmann integers in the sense that they're integer combinations of Grassmann generators. Like, see what I'm saying?
Yeah.
So the zi's are actually integers. Okay? Does that make sense?
Yeah, so it's like, I forget what they're called, but you have like complex numbers.
Gaussian integers. You're thinking of the Gaussian integers.
Yeah.
Right, these are the analogs of the Gaussian integers here. Totally. But either evenly many or oddly many Grassmann generators. But, there's your coset, right? And and we were working down here like, okay, so we can define an equivalence relation on this G. ABC is equivalent to A prime, B prime, C prime. If A minus A prime is in the even Gaussian integers, let's say, using your terminology, or if and B minus B prime and C minus C prime are element of that, and then I was like, actually this isn't quite right. Actually strike this. That's not what you want. What you want is that these are equivalent if they're representatives of the same coset. because this quotient, right?
Yeah.
It's actually a coset space. You're really looking at like XH. Well, XH. It's like X theta beta H. X theta beta H3Z or something like that. Sorry, there's a mixture of different discussions here we're trying to sort through. I still think it's useful. Okay, great. A little bit fuzzy here, but so maybe it's clear over here. So yeah, we're thinking, okay, so following Alice Rogers' paper, we'll let G be 1 x theta beta, where x is even, theta beta odd. Now, at the level of Grassmann components, they look like that. Ugh. All right, fine. And then we wanted to, like what does it look like? H12Z, like what are the Gaussian integers in this thing, basically? Well, okay, so going back over here, if I multiply these two things, right?
Yeah.
I get this. And so what I would want is that I would want x minus x. I would want x equal to x prime plus some integer multiple of Grassmann generators. I would want, this is a sort of heuristic notation for the, they should differ basically just by something in r sub cz or r sub az. Does that make sense?
Yeah.
So this is the product of, it works out to that, and so that would say that these things have to, these have to be again Grassmann integers, and we were able to, through thinking about that, derive the conditions she writes in her paper. Okay.
Wait, so R sub A, though, that's the anti-commuting Grassmann numbers?
Right.
I mean, yeah, super numbers.
Yes, super numbers. With integer coefficients is the,
Yeah.
Right. Ultimately, the point here is that the coefficients, we only need to think about them ranging over one unit interval, because different intervals we identify.
Yeah.
Because we're modding by integers. And so that's where the interesting new structure comes into play. Okay, so then we looked at Wikipedia. And in Wikipedia we found this wonderful thing, that in fact the Heisenberg integers can be generated from these guys, x, y, and z. In fact, z is equal to x, y inverse, x inverse, y inverse. These commute, and anything in H3Z can be presented as such. Guess what? We did the same for supernumbers. So, this is our typical, where is it? Basically, our point is we can use this playing the role of y, this playing the role of x. So instead of just putting a 1, we put a Grassmann generator into place. Put a Grassmann generator in place of that. And we can also get the z eta I is actually nothing more than x eta I y1 x eta I a inverse y1. That actually puts eta I up here like we wanted. And so we can get the Grassmann generator that we want in that position, or that position, just like we want. And so if you look at anything, any of the Grassmann, anything in the sort of this thing, H13, not R, but this one, H312Z, I can build them from powers of these 3x3 matrices with the Grassmann generators stuck in there. And so like an arbitrary thing in here, like this, can be written as an infinite product of these guys, those guys, and those guys. So I have an explicit sort of super analog to the Heisenberg 3-integer thing. I was kind of excited about. I don't know what to do with this. I just think it's a cool formula. I haven't really done diddly with it. But okay, so what I have not done yet is to find an atlas for this mod that one.
Wait, for what mod that?
For the
Oh, okay. So the
full the super Heisenberg, let's say the super Heisenberg 1-2 group mod the 1-2 Grassmann integers. See, I have to. I mean, Alice has something like 56.
56 charts.
Yeah, we'll have more.
Infinitely many more?
Many more. But it's countable. There's hope. And so here was a simple example of a kind of a stupid quotient in some sense. It got me thinking about super quotients. Like here's G1 R11, and suppose I want to just mod by take this as my my cosets, these horizontal lines, right? So this is H is x comma 0, where x is a commuting supernumber, and it gives us that. And so these are equivalent if and only if that's equal to that, which is to say that the difference is in there, which is to say, by the way, that beta is equal to theta, and the difference of x and y is a real commuting supernumber. And so this is really not that exciting. This quotient, G by H, is nothing more than R sub A, really, which of course kind of makes sense because I'm saying squish these lines to a point while you're just left with the anti-commuting axis. Now, what's perhaps more interesting is what if you don't squish the whole? What if you just squish one of the Grassmann directions or something,
Wouldn't that just squash one dimension? Like, go from R21 to R11, for example?
No.
No?
No. It does other things. It doesn't. What I have found is that I can compactify, let's say, some of the Grassmann dimensions, and I don't lose super dimension. Like I can wrap up like the A to 1 direction and A to 2 direction, but I've still got A to 3 through A to infinity and products thereof. And it's still an honest-to-goodness one-dimensional supermanifold. However, now it has non-trivial topology in those directions. And I do think I have coordinate charts. And the overlap functions are particularly beautiful and simple. They're nothing more than the identity shifted by a Grassmann generator. And those are clearly super smooth. So I think I even have... I have those things typed up. I'll have to show you, okay? But what I have... So, less greedy versions of this, I think I have worked out carefully at this point, okay? And I can get away with not that many charts. I think 2 charts will do it. But as I'm wrapping up more and more Grassmann dimensions, if I wrap up infinitely many, then I'm going to have, I think, infinitely many different charts to think about. But I don't think it's impossible. I think if we understand it carefully, I think we can actually sort through it. And with the right notation, we can argue, in fact, that we have a supermanifold with non-trivial fermionic topology, where the topology of the supermanifold is not at all the topology of the base manifold. And in my book,
It's 6 o'clock.
that's a supermanifold with kryptonite, which means We have killed the Superman functor.
Okay.
Which is my ultimate goal.
What is the Superman puncture and what is kryptonite?
Well, to me, kryptonite is something that Superman can't handle. Fair? What was this? This is the kind of domain stuff she does. No, I don't think I had the explicit transition functions worked out when I met with them that day. They came afterwards. I won't have one of these boards anyway. We gotta go. For now, I have an 8.